Okay. All right, everyone. So in today's lecture, we will continue discussing, we'll just quickly review refractive index, talk a little bit about absorption. It's not something that we usually discuss a lot in the labs, but it is important to know about it. And then we'll discuss the wave picture for reflection and refraction. And yeah, this was ambitious and probably not get to all of this, but we'll hopefully get to at least introducing Fermat's principle for propagation of light. Okay, so in the last class, we saw that because of the phenomena of scattering that occurs at a microscopic level when light travels inside a medium, and in the medium, if it's dense and homogeneous and presumably mostly transparent, things like glass or air is also a medium because it has molecules, obviously, and not just vacuum. Similarly, water, so on. All of these scattering is occurring on a microscopic level of the light, and that microscopic scattering gives rise to a macroscopic phenomena, which is that the light beam, the plane waves of the light beam, propagate with a different phase velocity inside the medium. And that phase velocity, as we saw, is given by c divided by n. So in free space, we know the speed of light is approximately 3 times 10 to the 8 meter per second. But in dielectrics, we call dielectrics anything that's sort of like insulators typically, right? You know that from 174. Most of them, if they're transparent, like water, glass, plastic, many clear plastics, etc. All of them will typically be described by the refractive index, and that refractive index then modifies the velocity, the phase velocity of light as c divided by n, and the quantity n is referred to as the refractive index or the index of refraction. And so typical examples are something like air, which is almost 1, almost like free space because it's just a dilute gas. Water is a little higher, it's 1.3. Glass is even higher, 1.5, and then there end up being many different types of glass, especially with modern technology and material science. We've learned how to fabricate glasses with all different types of refractive indices, and that's actually very helpful, as you'll see later on when we discuss creation of like various types of lenses and so on. Okay, so that was from last class. So now the one thing I want to point out is when the refractive index is now greater than 1. And we also talked about refractive index less than 1 and what that might indicate. As I said, phase velocity doesn't always imply that the information will travel at that velocity. But anyway, for Na greater than 1, it turns out the wavelength inside the medium will be lesser, shorter, or decreased compared to the vacuum wavelength. So when you think about light, electromagnetic light in vacuum, it may have a wavelength, so we call it lambda naught. Then it turns out in the medium, it's going to have a wavelength lambda naught divided by. Why is that? So I just put that up here. So let's say the incident medium has a wavelength lambda, that's the incident electromagnetic wave. And then we come into the medium, which is say glass or air, or whatever. And then it turns out that in the medium, the wavelength is shorter by this factor 1 over n. So it's lambda divided by n. And why is that? Well, the answer is we know the dispersion relation in vacuum, which is just a fancy way of saying we know the relationship between the velocity, the wavelength, and the frequency. Okay, so the dispersion relation in a vacuum is just c equals lambda times the frequency. Sometimes I'll use nu for frequency instead of f. F is another way to say frequency, but I'll sometimes use nu as well. So c equal to lambda times mu, right? So now if I divide by n on both sides, I get c over n, which of course is the speed of the light in the dielectric of refractive index n. And then on the right-hand side, we have a choice where we put that n. Okay, we can either put that n underneath the lambda, or we can put the n underneath the frequency nu. Okay, now the frequency f or nu from quantum mechanics, we can also think of that as defining the energy of a photon, right? We know that from Planck's theory of quantum of black body radiation and just generally that the energy of a photon of this frequency nu is given by h times nu. Okay, you must have heard this or seen this somewhere, but if not, I'll just let you know about it now. And the point is that E equals h nu. So the energy of the photon is not changing because it's just elastic scattering that's happening as we go along in this medium. So we instead have to conclude that it's the wavelength of the light, the wavelength of the phase fronts, the separation between the phase fronts that is changing by this factor n, okay, lambda over n. Another way to also picturize it, if you don't want to think about photons, is, well, think about an atom that's sitting in the medium. And in comes the driving electric field at some frequency nu. Well, what frequency is the atom going to respond at if it's not on resonance or whatever? Is it's going to respond at nu, right? That's what a damped driven harmonic oscillator does. The atom also is shaking the cloud of the ground state cloud, the vibration that I talked about, is also going to be at the same frequency as the incident light. So the output light will also be scattered and will come out at the same frequency nu as the incident light. So that's another classical way of thinking about why the scattered light is at the same frequency nu. Okay. All right. So this is a very important factor that you should keep in mind whenever the wavelength, when you're thinking about wave propagation in media, that the refractive index is also going to change the wavelength of the light. Okay. Another thing to know about, which, as I said, it's not something we often will do in the lab, although there may be one or two special projects where we think about it. But it turns out that again, the same idea of scattering, right? We've been thinking about elastic scattering, where the light is always, rescattered without any losses. Okay, it's scattered into other directions, perhaps, but there's no energy loss in the medium. Okay, all of the energy that comes from the electromagnetic wave gets transmitted outward as another electromagnetic wave. Okay, well, it turns out in many media, for example, metals is a common example, but there are many other examples, and even in like regular materials like water or glass, there is some loss. Okay, the atoms, when they respond, as you know, they have some damping, right? We talked about damping. Well, that, if you think about again like a frictional force, that implies that some of the energy is being lost to that frictional force that is needed to overcome that damping term. Okay, so in that way, we can just think about it in all those different ways. You can think about it through the lens of like, or through the picture of like some damping. You can think about it as a picture of like non-elastic scattering, etc. The end result is that the input power and the output power are not the same. Okay. And typically the way we characterize this is not super important for you to know, but I'm just letting you know because you may encounter it in other situations or somewhere in some other class. So this gave rise to something called Weir's law, which was because it was first discovered experimentally, that the output power is equal to the input power times e to the minus 2 alpha L, and alpha is called the absorption coefficient. Okay, so for conductors, and many obviously metals are very good conductors, it has very high absorption. Okay, this is why you don't see light going through a metal. Okay, it just reflects off the metal. So alpha is on the order of 10 decibels. Decibels is just a logarithmic way of describing that factor alpha. So it's like a factor of 10, basically 10 dB for every micron. So for every micron, the light power decreases by a factor of 10. So you can see within like a few lengths, of 1 over alpha, right? Or 1 micron is 10 is a factor of 10. 2 microns will be factor of 100, and so on and so forth. Okay. Dielectrics, on the other hand, have very low absorption. In fact, one of the key things that made optical fibers a viable technology is through very, very difficult and hard work in material science. Finally, people were able to create a glass, a silica fiber, which was having very low losses. So you can see the losses are 0.1 decibel per kilometer. Okay, so this is a huge improvement from what glasses used to have before this discovery or this invention was made. That got a Nobel Prize, by the way. Okay. To be able to create a material that had such a low loss was revolutionary, as you know. I mean, like now we have optical fiber that's transmitting data and everything else everywhere. Okay, so I find this graph very fascinating. That's probably the nerd in me. Okay, so this graph is so fascinating to me. The reason it's so fascinating is this is a plot of the absorption, or actually it's written as percentage of transmission rather than absorption. Shows you the transmission as a function of wavelength in our atmosphere. Okay. So look at this graph, and you can see there are many, many regions of the atmosphere where light just does not travel very far, right? The percentage of transmission almost plummets to 0, in say a wavelength range of like say 2 point something microns or 1.5 microns or 1.3 microns, so on and so forth. And you can see that the region where there is the most amount of transmission is 400 to 700 nanometers. We're looking mostly at visible light here. I mean, we could also go to the ultraviolet, but that also has similar problems. There's going to be a lot of absorptions and things like that. So it turns out there's this very narrow window in our atmosphere where light propagates almost with no losses. And of course, biologically, we evolved for our eyes to be able to perceive those wavelengths. Most specifically, right? All of the things, the machinery in our body, this is an amazing thing, we'll talk about it later, is adapted so finely to pick out this wavelength region in the atmosphere for billions of years. And it always fascinates me because I'm obviously, we have extrasolar planets. I mean, even before that, we speculated about other planets, long before we discovered that there were other planets. Just think about like what, the absorption spectrum might be in those planets, right? And if they're composed of different gases and life arose in those planets, what would they have to adapt for? And how would that change the life on those planets? And, the development of a civilization, for example. Those of you who are fans of hard science fiction, you might be thinking, there has to be some stories. There are many stories actually already about, planets where, for example, only radio waves could propagate easily. Okay, or radio waves couldn't propagate, things like that. And so that's some of the stories. And then recently, I don't know how many of you are fans of The Martian. Have you seen The Martian movie or read the book maybe? Okay. So Andy Weir, the guy who wrote The Martian, he also wrote another book recently called Project Hail Mary. Okay, and he talks about, without giving away too much about the plot, there's some interesting stuff about absorption and converting energy and so on in there. So encourage you to go read it. It's a nice book. It's a fun read, summer read at least. Okay. All right. So anyway, I think this is a very interesting topic in general about what might be going on in extrasolar planets and how that might affect life. Okay. So I will just sort of conclude our investigations or our discussions of light interactions with matter with just this statement again. I make this statement again, and hopefully by now I've made it clear or made it more believable to you that all of the light propagation phenomena that we have discussed, whether it's the color of the sky, whether it is the fact that there's an index of refraction, whether there's absorption, whatever, all of this can be viewed as a manifestation of scattering at the microscopic level. Okay, so having said that, now I want to discuss something that you already heard about probably in the lab, which is reflection and refraction. Okay, we've talked a little bit about reflection and refraction, but now I want to convince you that actually the laws of reflection and the laws of refraction can also be obtained from this wave picture for light. Okay. So far we've looked at what happens inside a homogeneous transparent medium. We essentially assume the medium extends from minus infinity to plus infinity and just looked at what happens inside that medium to the wave propagation. But what happens at the boundary between two different media? Okay, so we have a medium 1 and a medium 2, and they have, let's say, different refractive indices, or they have different properties. Maybe one is a piece of metal which has very high absorption, but does have, something else which we know very well, which is reflection. Okay, so what's going on, and can we derive some laws about what's happening at the boundary between these two media? Okay, firstly, I will just state without proof. I mean, you can think about this. It may take some work to convince yourself, but we'll just accept this and move on. That really what all that matters is something like a boundary layer at the interface between the two media that really does most of the scattering, that does not cancel in the backward direction. Okay, so we already know that most of the time when there's a dense medium, most of the light propagates in the forward direction. Okay, but in the boundary, as you can see, it's unbalanced, right? There's a bunch of atoms at the boundary where they don't have a corresponding atoms to the left of them. For example, if the boundary is over here to my left, there are no atoms of the same type. Okay, so there's a clear discontinuity in the number of atoms or the type of atoms, etc. And then the scattering is also going to be different, okay, from these boundary layer of atoms. So these boundary layer of atoms, they're of course going to scatter in the forward direction. That gives rise to our transmitted beam. But in the backward direction, there's nothing that's going to cancel out their scattered light. Remember, we were talking about how the propagation of light goes in the forward direction is because there's all the lateral scattering and the backward scattering, etc., gets suppressed by the interference between different atoms. Okay. So, and now you can ask yourself, okay, so what does that scattering do? Well, it could have many different consequences, and that kind of depends finally on the details of the surface. Okay, so just to give an example. Okay, the zoom is okay, so as I said, there's this boundary layer, but okay, so depending on the surface, if you have a very smooth surface, okay, and here's the surface and here's the medium, okay, over here, so this has refractive index. And for now, simplicity, we'll take air on this side and we'll assume that this has refractive index 1. Okay. Then as this beam comes in, and we'll prove in a minute that there is this reflection. But this reflection could, of course, go off in many directions, right? I mean, you have many atoms, okay? And I'm just drawing them well spaced apart, but of course, they are very finely spaced together in a medium, right? The spacing between atoms in like glass or diamond or any other insulator is much, much smaller than the wavelength, right? So these atoms are scattering the light, and if the surface is also very smooth, okay, very, very smooth, meaning there are no fluctuations in the surface on the order of a wavelength or more, then it turns out that there'll be only one beam going backward. Okay. So I told you that there is a scattered light coming back from the atoms, and these atoms, when they scatter back, you could ask, well, maybe the scattering will give rise to a lot of different beams. It turns out no, it doesn't. When the spacing between these atoms is very small, much smaller than a wavelength, it turns out that the reflected beam only goes back in one direction, or you can think that the sum of all the scattered wavefronts goes only in one direction, which is this reflected beam. Okay, so there's an incident beam, a reflected beam, incident beam. And of course, this incident beam is along the k vector for the incident wavefronts. So there are wavefronts coming in that are perpendicular to that. Similarly, there are wavefronts which are perpendicular to the reflected beam. And that's what we'll show in a minute in the wavefronts.
So at the boundary, so we just have so we just check the magnetic field and electric field, and then checking in the perpendicular and
the parallel directions, right? Yeah. So of course, there's also a transmitted beam, which I already told you about. For now, I'll just draw it like this, but we'll show in a minute that it actually bends up. Okay. It doesn't just go straight as it's shown. So yeah, maybe I should show that. So there is also, so that's the normal to the surface. The normal meaning perpendicular to the surface. So this is theta t, the transmitted. This is theta I, the incident angle, and then this is theta r, the reflected. Okay. So this is for a very smooth surface. Now I should point out that many surfaces are not smooth. Okay. Lots of things are not smooth. Your hand isn't perfectly smooth. The skin, has fluctuations on it, which are much greater than a wavelength, for example. Okay. So when you have some kind of, a piece of paper, for example, even though it looks very smooth, has very, very imperfections and roughness on a scale that is comparable to the wavelength. And so then what happens is when the incident beam comes in, you may get a reflected beam from here, but you also get other reflected beams. In fact, it becomes so diffuse or scattered out in all different directions that you don't get a sharp reflected beam coming off of that rough surface. This is called diffuse reflection. And this, where you get a sharp beam of light coming out, is called specular reflection. Okay.
So the reasoning is the surface is not smooth, not really.
Exactly. That's what gives rise to all these different beams of very weak. They're very weak, so they don't have a lot of power in them. So our eyes are usually too weak to perceive that there's all this scattering going on in all these different directions coming off from the surface.
But for grating,
grating is different. A grating is arranged so that the grooves in the grating are roughly on the order of a wavelength.
Yeah.
And that ends up giving rise to sharp beams, but also you get multiple sharp beams.
Yeah.
So it's not just one sharp beam, but multiple sharp beams. We'll come back to a grating later on in the class when we discuss diffraction. So yeah, this is like, you can think of it as the roughness is like usually on the order of more than a wavelength. It's also very random compared to a grating, which is very ruled in a specific regular pattern. So anyway, so this is diffuse, this is specular. Okay, so that's what I have to say about reflection in general. By the way, things like this have been used, for instance, in the stealth fighter. So when a stealth fighter is made, the way they made it was to have surfaces that have diffuse reflections and reflections going off at different angles of the radar energy. So the radio waves that are being used in a radar get scattered off into all different directions, so you don't get a strong return beam coming back from the stealth fighter. And that's why you get, the stealth fighters don't show up on radar in the same way as they do as other aircraft. Okay, so now we'll discuss the wave picture for the reflection, having understood what happens. So again, we have the incoming incident beam with its wavefronts that I just drew there, and then we have the outgoing or transmitted beam, which is also called the refracted beam, which has its own wavefronts and it will bend, as we'll just show in a minute. While the reflected beam, as shown here, goes off in this direction, and there's only one because of this property that I just talked about. When the surface is very smooth and the atoms are spaced much smaller than a wavelength, then you end up with getting only constructive interference in only one direction. Okay. So if I take a closer look at this interface, and now instead of drawing all the atoms here, I'm just going to draw a line of atoms to indicate these are the atoms that are contributing to the reflected beam. Well, you can see here that when the incident wavefront BA reaches this atom over here, right? Okay, so A is one of the atoms or a point on the interface, okay, and B is the other end of the beam, which is the wavefront, okay. And now let's run the wavefront forward by a time t, okay. B now reaches the point D here on the surface, okay. At the same time, because now, as I've just said, the A, this point A from which the reflection is taking place, that wavefront would have propagated to the point C, okay. So since this wavefront is the same wavefront, basically it's just being reflected and is coming off, the distance BD must be equal to the distance AC, right? Because the phase has to remain the same for the phase front to propagate together, okay? So if that is true, if BD and AC are equal, and we know this distance AD is common to these two triangles. So look at the triangle ACD, right? That's this triangle. And the triangle ABD. Okay. The angle that these two are making, so you can see here, ABD, this angle BA is theta I, and the angle CDA, that is CDA, that angle is theta R. This is the angle that the wavefront makes with the surface. Okay. Similarly, BAD, this angle over here, the angle that the wavefront makes with the surface is the incident angle. And we just showed that BA and BD and AC are the same distance, okay, by the argument that this belongs to the same wavefront. Therefore, immediately you can show that, any number of different ways. You could take the sine of these two angles and calculate from the hypotenuse or whatever, whichever way you want to do it, you immediately see theta I and theta R have to be the same. Is that okay for everyone? If you want, I can go through the steps. Just take the sine, okay, or use similar triangles. These two distances are the same. BD over sine theta I must be equal to CD over sine theta R from similar triangles. And therefore, by that construction, theta I must be equal to theta R. Okay.
Yes, so I have a question. So, is the surface we're talking so far all materials, not metamaterials, right?
Yeah. Yes, I'm just assuming that the material is made of atoms, which are all very, very finely spaced compared to wavelengths, and none of that other stuff like metamaterials is important at this point.
Yeah. I came across the review by Xian Zhang at Berkeley before, so it's very interesting. Okay.
Yeah. I'm glad you're reading beyond the course, but let's just stick to this. Okay, so we have talked about the wave picture for reflection. Sorry. But I want to now also point out that it turns out that most of the time, it's easier to discuss these kinds of effects in the ray picture. Okay, so recall rays we define as being normals to the wavefront, okay, and the trajectories of the particles of light, and usually they're just parallel to the k vector of the wavefront. Okay, the k vector, remember, is a normal to the wavefront surface, and in isotropic homogeneous medium, rays and k are always parallel to each other. Okay, here are some more properties that I laid out for you earlier. So if I were to now rewrite or redraw our wavefronts and now draw the rays, here are the rays. Okay, they're normals to the wavefront, right? They're coming in, and then they're reflecting off this interface, and again they're normal to the reflected beam. Okay, so that's what is happening to the ray picture. And again, earlier we saw that the phase fronts or the wavefronts have an angle theta with the surface, right? And if I rotate everything by 90 degrees, right, which is if I rotate the wavefronts, or if I think about this ray, which is perpendicular to this wavefront, similarly, if I take the normal to the surface by the same argument, because the wavefront is having an angle theta with respect to the surface, the rays, which are at 90 degrees to the wavefront, must have an angle theta I with the normal to the surface. Okay, just a rotation by 90. Okay, same thing on the reflected beam side. Okay. So we also can state another law of reflection, which can be proven more generally, but it's fairly obvious from this geometrical argument that the incident ray, the reflected ray, and the normal to the to the interface surface, that is this normal that I've drawn here, all have to lie in a plane, and that plane is called the plane of incidence. In this case, the plane of incidence is simply our screen over here, but you can draw it in 3 dimensions. For example, like this over here. Okay. So here is the interface. I mean, imagine this were our surface over here. The normal to the surface would be going up, right? And if I had an incident beam like this and a reflected beam like this, they would have to lie in the same plane, cutting through the surface, which is what is drawn over here. Similarly, we can do the wave picture for refraction. Okay. All right. So now I'm looking at the transmitted beam. Okay. And now again, I take that wavefront BA, just the same wavefront that we were talking about earlier. Okay. And again, it makes the angle theta I with respect to the surface. Okay. Now, in the time delta t, okay, B goes to D. Okay. Let's say that it takes a time delta t for the incident wavefront from the point B to go to the point B. In that same time, the wavefront A goes to the point E inside the medium. Okay. Of course, we know the wavefront is traveling with the phase velocity VI, or just V, V1, whatever you want to call it, in the first medium, which is the incident medium. This is another, sometimes our language in this optics is not very good. The incident ray is traveling in the incident medium, and the refracted beam is traveling in the transmitting medium. Okay. I won't often use this language. Okay. Usually I just say medium 1 and medium 2. But okay, just so you know that this is how it's written in many textbooks and so on. This is the incident medium, this is the transmitted or the medium of refraction, etc. So in this transmitted medium, we know the velocity of the wavefront, the phase velocity is v subscript t. Okay, and we know v subscript t. Well, let's say this is glass and this is air. V subscript t is higher or lower than v subscript I. What do you think? Anyway, low.
How do you know that AE is not parallel to BD? Just ignore that. Assume that we do not know Snell's law. How do you?
I have not said anything about Snell's law, but I have argued that the distance AE now must be smaller than BD because the velocity is less inside this medium.
But how do you know? How did you figure out that they are not parallel?
Well, if this is the same wavefront, right? This is the same wavefront, right? It has a constant phase.
Yes.
So if this distance is shorter, then I have to draw the wavefront from the point D to the point D. So it must be bent compared to the incident angle. Okay. So BD, as we just said, has a distance VI times delta T. AE has a distance VT times delta T. Okay. So let's show that in a little bit more detail. Here's our interface, okay? And here is, I just drawn now the wavefronts coming in. Okay. Here's the point B, here's the point A. Then this distance BD is VI delta T. And this distance AE, this distance is VT delta T. Okay. This angle is theta I. Okay. And this angle over here, I'm calling as theta T. Okay. Everyone with me so far on this drawing? Is the drawing clear to everyone? Have I drawn it big enough for everyone to see back there? Back? Yeah. Stop me and ask if something is not clearly visible. Okay, so now on these two triangles, again, this triangle over here, ABD, that distance AD is common with the distance AED, with the triangle AED, right? So these two are, if you think of this big, what do you call it? Quadrilateral, some word, rhombus, something. It's not a rhombus. Anyway, so in this quadrilateral, this distance AD is common to both the triangles that make up this quadrilateral. So we can equate anything that comes from AD, and remember this angle is always 90 degrees because of the way we drew it, it's a face front, right? So we can, for example, let's see, and we want to relate that to BD, so sine theta I is equal to BD divided by AD from the top triangle, right? Similarly, sine theta T is equal to AE, again divided by AD. Okay. Therefore, I can get rid of AD simply by bringing AD over to this side and here and say that BD divided by sine theta I is equal to AE divided by sine theta T. Okay, we just said that BD is just VI delta T by sine theta I is equal to VT delta T divided by sine theta T. So delta T's cancel out. Okay, and so now we are left with this equation: VI over sine theta I equals VT over sine theta T. I want to write this in terms of the refractive index. for which I remember now that VI, or sorry, NI, the refractive index, is C divided by V. We know that VI is, okay, either way, okay, whichever way you want to write it. I guess we are writing for VI, so I should write the velocity is just C divided by the refractive index, and the velocity in the transmitted medium is simply C divided by the refractive index in the transmitted medium. Substitute for for VI and VT, and we end up with NI sine theta I equals NT sine theta T. Okay, so this is now Snell's law, right? Okay, Snell's law of refraction, and he found it through experiments. Okay, and now we have derived it using the wave picture. Any questions? We've talked about scattering from like molecules or fluctuations that are smaller than a wavelength. Oh, sorry. This is just to summarize our statement. There's supposed to be an equation. But anyway, you have the equation. It's the Snell's law that was on the chalkboard a minute earlier, which you all probably know. Okay, so I just want to conclude our discussion of this wave picture of reflection and refraction by just giving some sort of overview of what happens in other regimes. Okay, so we've mostly been looking at scattering from atoms, molecules, or we talked about like anything that's really smaller than a wavelength, density fluctuations in a gas or a fluid through Einstein's Smolachowski can also be thought of as undergoing Rayleigh scattering or elastic scattering. Okay, what happens if the molecules are now larger than a wavelength? Okay. So when particle size is greater than the wavelength, well, in physics, we just like to reduce everything to some problem that we have already solved. So what we do is we break up that molecule into smaller parts, which are less than a wavelength, much less than a wavelength, and find the solution for each of those, and then add up all those things. We're not going to do those. That's obviously a more graduate level problem, but we can just have some general idea of what will happen, okay? So scattering from one part of the molecule might be out of phase with another part. So what ends up happening is that as the size of the particle increases, those blue wavelengths will tend to get more quickly out of phase because they have shorter wavelengths, right? So therefore, they tend to like get out of phase more quickly, okay? Because they're short. So even a small phase difference, small distance difference will lead to a larger number of wavelengths can fit inside that, okay? So we expect, in fact, that the red wavelengths will scatter more. Okay, so in fact, the red wavelengths will start to scatter more than the blue wavelengths once we get to larger particle sizes. Okay, but it turns out that will also happen in the forward direction. So it kind of gives you a reddish hue to both the forward and the off-axis or the lateral scattering. Eventually, of course, at some point, all the wavelengths will scatter with equal efficiency and predominantly in the forward direction. And an example of this is the color of milk, which is white, because the fat globules that are floating in milk is basically just suspension of some fat inside water. That's what milk is. Those fat globules are much larger than a wavelength. Okay, and therefore that's why it looks predominantly white. Okay, and this was first found experimentally in 1869 by Dinzel. Okay. What about when the particle size is on the order of a wavelength? We've talked about particle size much smaller than a wavelength, and now I have told you what happens when particle size is much greater than a wavelength. And then, of course, there's an intermediate regime. What happens when they're on the order of a wavelength? Math is very complicated. This is a graduate school level problem. This is called Mie scattering or Mie scattering, I think. I never know how exactly to pronounce it. Gustav Mie, he first published on this regime. And there's a lot of like effects here. But essential idea is that it only depends weakly on the wavelength and becomes completely independent of the wavelength when the particle size is increasing. By that I mean it's on the order of a wavelength, and as it gets bigger, it starts to become independent of it. It tends to be stronger in the backward rather than the forward direction, which is kind of an interesting and weird effect. So for example, again, examples of what this does, white garbage bags can look pale or blue-white in a scattered light, but orange, and obviously then they look orange in the transmitted light. Okay. And that's because they contain titanium dioxide nanoparticles that are about 200 nanometers in diameter and scatter bluish white. So that's why they look like this in the scatter.
This quantum mechanical scattering, so what way
this is B scattering, it's not quantum mechanics. It's just entirely due to electromagnetic waves scattering. Okay, so what happens for particles much greater than wave? Talked about different regimes here. We said, wavelength atom size is much smaller than a wavelength, atom size greater than a wavelength, and atom size comparable to a wavelength. Now I'm talking about atom size much greater than wavelength, say 10 or 100 times greater than wavelengths. Okay? We can come back to ray or geometrical optics. Remember, initially I said that the ray or geometrical optics picture is what predominantly we see when we look around, because most of the things that we observe with our, on a human scale, all tend to be much greater than a wavelength. Okay? And similarly, any particles that are much greater than a wavelength, and say 10 is just some limit that I picked out, but it's probably true that for anything that's on the order of like 10 times the wavelength, 5 microns, 10 microns or higher for like green, green wavelength is a predominantly sunlight centered around that. So anything like that is going to be, pretty much looking like a ray optics picture. Okay. All right. So that kind of concludes to some extent the discussion of scattering and how it gives rise to various phenomena. Like, we've talked about many of these examples already, so I won't go over them again. So now I'm going to enter the ray or geometrical optics picture. Because basically, as we said, for most phenomena that we encounter in life, it's important to know the fundamentals. Like, okay, we know why there's a refractive index. It's because there's a phase shift of the scattering from the atoms or the molecules. And that phase shift gives rise to a reduced phase velocity inside materials. But now that we know that there is a reduced phase velocity for the wavefronts, all we care about now, if we want to predict what is happening to the rays or to the, if we are using objects that are much greater than a wavelength, 10 times greater or bigger, then we just need to worry about how to understand geometrical optics. Okay. And so even though the term geometrical optics seems like, oh, I should just need geometry to understand this, you'll see we use a lot of geometry, but it's still very interesting and has a lot of consequences for how we make images and how we understand the propagation of light. And this is probably what, for any optical system, anything you're trying to understand or sketch, in the beginning, the first thing to do is always to draw the ray picture, the geometrical optics picture. And then only then we might add in corrections through waves or other kinds of scattering theory and so on. So the first thing to do is always understand the geometrical optics picture and understand how it works before you think about what might be happening in the wave phenomenon. Okay, so I just want to introduce in the few minutes that I have the most important principle in array optics. This is like the fundamental principle that allows us to understand how rays propagate. And this is called the minimum path Fermat principle. Okay. So let's look at a light ray, which is in some medium with a variable optical refractive index, okay, n, which is a function of r. Okay. So of course, in one way to solve the problem of the ray trajectory through this medium would be to break it up into smaller pieces. At each piece, we can think of it as like having a medium of refractive index n1 and n2, and just solve for what happens to the ray, because it's going to have Snell's law. It's going to follow Snell's law at each of those interfaces, and then to predict the curvature of the ray, you just do a line integral or something along that path to find the answer for the trajectory. So that's certainly one way to do it, and that's almost exactly how we think about things in classical mechanics. We look at each small instant of time for a ray or for a particle, whatever, as it's propagating. We write down the differential equations. In this case, the differential equation is just Snell's law, right? Basically, it's just Snell's law at each little tiny piece. And then you solve for the path of the ray. But instead, what we're going to do is we're going to say that our Fermat said, and this is the same Fermat who did Fermat's last theorem, said that he could prove that theorem. This Fermat, what he said was the path gamma that the ray actually follows is the one such that this integral, this is the line, the integral over the path gamma of the refractive index times dl. Okay, so the distance is of course dl. So if I didn't have a refractive index, integral of gamma over dl would be simply the length of the ray, right? It would be just how much this ray p to p prime, how much path length this has taken from p to p prime. Okay, just distance, geometrical distance. Sorry, let me just finish before you ask a question. But instead, we multiply it by also this factor n of r, okay, which is the refractive index. And his statement is the path that the ray follows is such that this value, integral of gamma n of r dl, and this number n times distance is called the optical path length. This is very, very important. We're going to use it all the time, not only in geometrical optics, but in wave optics as well. N times the distance, the optical path length, is very critical thing to know. And the idea is that he's saying that it's the actual value, the path that is actually followed, the one that the light actually follows, this integral must be smaller than all the other possible paths from point P to point P prime. Okay, what's your question?
So my question is for this is least action principle.
Yeah.
So how do we get this from the so how do we get this from mechanics? So like the Hamilton and Jacobi equation.
Right. So in electromagnetism, of course, we had to start with the Maxwell equations.
Yeah.
And then when we specialize to the wave or to the ray optics picture, you derive something called the iconal equation, okay, or Helmholtz iconal equation.
Yeah.
That Helmholtz iconal equation turns out to look just like some of the Hamilton-Jacobi equations. Okay, and from that we can then show that there's an equivalent least action principle, okay, or least time principle. Okay, and what is the analogy? If you've taken a mechanics class that's a more advanced, classical mechanics, you might have seen a similar principle called the minimum action principle. Has anybody heard of the minimum action principle? Everybody? Yeah, I see some nods. Not everyone, maybe. Okay. Because the corollary is what is the least time or the least path length from one point to another? Well, in a constant refractive index, it has to be a straight line, right? Because this n is just a constant. I just pull it out. Then what's the least? What path has the least distance from point P to P prime is always a straight line path. Okay. And the consequences of this, as we'll see, are also the laws of reflection and refraction. You might also see this principle formulated as a least time principle. Why is that? Because, of course, n, which is the refractive index, is written as c divided by v, right? The velocity in the medium. So if I take out the c, which is just a constant, I get dl divided by v, the velocity, so that's a time. So sometimes you'll hear this referred to as Fermat's principle of least time, okay? And so that's, okay, so I'll just stop there for today. I think this is an amazing principle. In general, minimum action or least, these kind of principles are like really fascinating to me. So I'll talk a little bit about that, and then we'll go through some consequences next time. All right, thank you.
Yeah.
So let me just summarize today's class. Okay, yeah, that's a summary for today. And if you have any questions, it's